In this video, I will go over the homework that is right after the lecture 0.4.1 called the definition of a derivative. And I don't expect this homework to be too intense, as there is only so much you can ask about the definition of a derivative. But what you expected to know here is the geometric and the geometric interpretation of a derivative and the definition of a derivative as a limit in and there is more than one way to write that. You are also expected to know the derivative of all basic functions, whatever they are, and let's see what's on the homework. First it says using the definition of a derivative, and let me write out a definition or two definitions of a derivative. So one says that the derivative of a function at a point is the limit as x approaches to a of f of x minus f of a over x minus a. And this is not the working definition, so this definition does make sense as the difference quotient, but the following is the working definition of a derivative of a function at a point. So we introduce h, and here we rewrite the difference quotient using the h notation instead of x. So this is what we have. So now in our case, a is equal to -1, and f of x is given to be 2 over x minus 1. So we're going to find the derivative at -1 as a limit as h goes to 0, and here we're going to plug in, so I guess we can spell it out, right? So what's f of a? F of a is f of -1. In our case it will be 1 over, not actually 1, 2 over -1, so it's -1. And we also want to, I guess, spell out what f of a plus h would be. In this case, it will be 2 over a plus h. We plug that in for x, but a is given, a is -1. So this is what we have. And now we're setting up this limit as the limit of f of a plus h, so it's 2 over -2 plus h, minus f of a, which is -1, and we divide all that by h. Now here you have to make a decision, because now it's just a limit problem. You have to make a decision whether you're going to look for this limit graphically, numerically, or analytically. And I'm going to show you how to do it analytically, but then we'll check the work with a quick graph. So analytically, I'm going to simplify the expression inside of the limit, and it looks like we have to do a common denominator in the numerator. So we have this fraction plus 1, but instead of 1 I'm going to write it as h minus 2 over h minus 2, and all that divided by h. Now we can combine the fractions in the numerator. So we have 2 plus h minus 2 divided by h minus 2. We have that written as a single fraction, and then all that divided by h, and once again reducing these 2's, and we have h divided by h minus 2, and I'm just going to write it as a single fraction. But you can see how h's are cancelled now, and we have limit of 1 over h minus 2 as h approaches to 0, and that is simply just negative 1/2. So the answer is negative 1/2. Now, how do we check our work? Let's go to Desmos. And we're going to open the graphing calculator. And all I'm going to do, I'm just going to graph this function. So instead of h, I'm going to use x. So I'm going to write 2 divided by negative 2 plus x minus 1. And all of this divided by x, which is h. And remember, we're looking for the limit of this as h goes to 0, but h is now represented by x. And you can see that the limit here as h approaches to 0 is equal to negative 0.5. So again, don't get mixed up. We note this is the function of h, and I just used x instead of h in Desmos. So one way or another, the answer is negative 1/2. Or not. Let's see, where did we go wrong? I see. For some reason I thought it was x minus 1. So such mistakes are inevitable, so we do make typos here and there. So let me just grab a red pen and rewrite my solution here. So what changes? This becomes negative 2. This becomes negative 2. So f of a is not negative 1 anymore. It's actually a little bit more complicated now. So it becomes negative 2/3. And here we have, this is negative 2, right? So this is now negative 3. So it's negative 3 over here. This is negative 2/3. This is h minus 3. And here we have, so this is h minus 3, but we have to have this coefficient here 2/3, right? So we still have 2 over here, 3 over here, and we're just going to multiply this by 3 as well, as a part of finding the common denominator. So when you find the common denominator, it's going to be a 6 plus 2h minus 6. So the 6 will still be cancelled, but now we have 2h in the denominator, and we have 3 times h minus 3 in the denominator. So fixing your own errors, it's a skill, and this is why I didn't stop and start recording all over again, because I want you to see how to react to your own mistakes. Just stay calm and try to fix your mistake in the most efficient possible way. So here what we have left is 2h, we have h minus 3 here, and we still have 3 in the denominator, and the final answer will be 2 over 3 times h minus 3. So the final answer is, when we plug in 0, we get negative 2 over 9, and that's the final answer. Now again, we can check again, because we weren't working with the right function here. So we're going to do 2, we're going to plug in negative 3 here, we're going to do negative 2/3 here, and we're going to divide it by h, and the limit at 0, it's, of course, the function itself is undefined, but you see the limit is negative 2 9ths. Now, to get a better understanding of what's going on here, we can graph this function. That's fine. There's nothing wrong with graphing this function. We're talking about the slope of a tangent line at this point. And if you were to guess this slope, how would you do it? You'll just graph some y equals mx plus b, and b is the slider, right? So as we change b, we want to have we want to align this and find the tangent line at the point at x is equal to -1. So we're actually looking for it here. So the easiest way to do that is use the point slope formula and write the... I'm just going to write this formula here. X minus a. We're going to add the slider a, and this is the line that represents the slope, and we want to set a to be equal to -1, and we want to, basically the question is asking what's the slope, right? And if we set the slope to be -2/9, that should be the right answer, as we can tell. Now the slope is actually equal to the derivative of the function at a. So you can see here how intelligently use technology to answer your own question. At this point, we don't have to do it in real life. You rarely do it using the definition, but so let's just remove this, and this pretty much is the template that we can use to answer all such questions, if there are any in the future. So let's submit this. Excellent. So did I forget to change the answer? I guess I forgot to retype the answer. Well, lesson learned. So the correct answer, so we actually did get the correct answer, we just didn't type it correctly. So the next problem, we're not going to be doing it by hand, we're just going to be using this template. So my function is 2 minus 4x squared, and we're looking for the slope of the tangent line when a equals 2, and this is what the tangent line looks like, and this is the equation of the tangent line, and the slope of the tangent line is given to us right here, -16. So it's okay to make mistakes here and there, but we want to get out of this homework being comfortable with at least the definition of a derivative. Same here, what we're going to do is we're going to change the function. And again, if you're doing this at home, you can just open Desmos and type exactly what I typed here, and use it as a tool to help you answer these questions. Again, we're not interested in doing all these steps by hand, we're more interested in actually understanding what's going on. In this problem, we have a function, radical function, and at x equals 5, we're looking for the slope of the tangent line, and we found it. Same here, but we have a linear function, and it's kind of redundant to look for the slope to the graph of a linear function, because the slope of the tangent line is the function itself, so the answer here is just -1. I think it's just giving us a second chance on that question. The answer is what, -2/9? Oh no, last time it was at -1, this one is at 1, so the answer is -2. And we finished one objective, so let's continue to the next one. Moving forward, I believe you would be able to skip the objectives, the ones that you're getting stuck on, and move on to the next one. Here we're looking for the derivative of a function, And in this case, since we're not looking for the derivative of a function at a point, and we're looking for a derivative function of a function, we actually have to do this by hand. So let me scroll down and let's find the derivative of this function. And in this case, it may imply that we have to use the definition of a derivative. That is, we have to set it up like this. H goes to 0, and we have to set it up of f of x plus h minus f of x divided by h. So if we do that using the definition, here's what we have. We have limit as h goes to 0, h in the denominator, f of x plus h, so we have negative 4x plus h squared plus x plus h plus 5, and now we're going to subtract the function itself. So we're going to subtract negative 4x squared plus x plus 5, and if we carefully distribute everything and combine the like terms in the numerator, we will learn that a lot of things will cancel. So here we have negative 4x squared minus 8xh minus 4h squared plus x plus h plus 5. And here we have plus 4x squared minus x minus 5. I'm just distributing the negative sign here, here, and here. And now let's combine the like terms. 4x squared cancels, plus x minus x cancels, plus 5 minus 5 cancels. And what we have left is negative 8xh minus 4h squared plus h, all divided by h. And notice how every term in the numerator has h, so we can just divide everything by h. So we have negative 8x minus 4h plus 1. And when h goes to 0, this term goes to 0, everything else remains. So the final answer is negative 8x plus 1. You can also notice that there's an easier way at this point to obtain this answer, but we're just going to stick to the basic definition, and just for the sake of showing an example of how it works. In real life, we don't do this type of problems using the definition. Another one, they want us to use the definition. So let's scroll. Let's scroll this down and let's find the limit of, let's find this derivative using the definition. So here goes f of x plus h minus f of x divided by h, and we're going to plug in, instead of f of x, we're just going to do this, right? And we're going to divide it by h, and that's easy to plug in. But for f of x plus h, we're going to write the same function, but instead of x, we're going to put x plus h. And we have a what's called complex fraction, so we're going to write it as a simple fraction with one numerator and one denominator. So we have to find the common denominator, and it's an algebraic task which I don't really want to spend too much time explaining, but this is how we find the common denominator and subtract two fractions with different denominators. And now, instead of actually writing all over h, I'm just going to use the property of fractions. That is the fact that a over b over c is the same as a over bc. That's a well-known property of a fraction. So instead of writing all over h, I'm just going to put h here in the denominator. And now we need to simplify the numerator. So we have 2x minus 12 minus 2x minus 2h plus 12. So you see how 2x gone, minus 12 plus 12 gone. So we only have negative 2h. And we can now cancel h here and h here. So after everything is simplified and reduced, we have the limit as h approaches to 0 of negative 2 in the numerator, x plus h minus 6 in the denominator times x minus 6. And when h goes to 0, we have nothing left but x minus 6 in the denominator multiplied by itself. So this is the final answer. So minus 2 divided by x minus 6 squared. So again, when you're doing this homework in Calculus 1, you're not really given an option of using anything but the definition. However, in this class, which is Calculus 2, it's totally fine if you just don't use the definition and use the properties. Although we will talk about the properties, using the properties later on. We'll review that topic in the next lesson. Let's find the derivative of this function. It's the limit as h approaches to 0 of, again, f of x plus h minus f of x divided by h. And in this case, we have f of x plus h. So let's plug in what's easy. H is easy to throw in there. Square root of x minus 6 is easy to throw in there. And now we're going to put f of x plus h. So instead of x, we just put x plus h. So this was relatively easy. So this is the limit that we're trying to find. And we notice how we have a radical in the numerator. And it's a very standard problem. So we're just going to rationalize the numerator by multiplying the numerator and the denominator by the conjugate. So it's going to be x minus 6, the same thing in the denominator, so it doesn't change the overall value of the expression. And what happens now is that in the numerator we can apply the difference of squares formula and get rid of the radicals. So we have simply x plus h minus 6 minus x minus 6. But in the denominator we still have all that craziness. So we're just going to copy it over. And we can see that this x will be cancelled with this x, this 6 will be cancelled with this 6, and there's nothing left but h, but that h can be reduced with this h. So at the end of the day, there's nothing left there. So we write 1 over, and we copy this expression again. So when x goes to 0, when h goes to 0, there's nothing really left here other than the two radicals of x minus 6. So this is your final answer. 1 over 2 square root x minus 6. And I bet there is more where this one came from. So let's just, I'm going to start skipping steps because we definitely seen rational function before. It was right here. So similarly, we can work out this one, except instead of number 2, we're going to have number 4, and instead of negative 6, we're going to have negative 1. So the final answer will be negative 4 divided by x minus 1 squared. This is called taking advantage of the pattern. And we got it. We saved time. Oh, this looks like an exciting exercise. The graph of the function is shown below in blue. Drag the black movable point situated on the x-axis to select the x-coordinate where the function is not differentiable. So we know function is not differentiable when the tangent line doesn't exist. And the tangent line may not exist for several reasons, one of which is that the function is not defined at that point, and the other reason is that the the tangent line is actually a vertical line. So in this case, like this crisp right here, it's a well-known pattern which tells you that there is no tangent line, or in this case, if there is one, it looks like it's a vertical line, so either way, the derivative does not exist at this point. Let's look at the other one. This is an example of the previous one was an example of a crisp where tangent line doesn't exist. This is an example of a vertical tangent line, so derivative does not exist. And not even that, like in this case, the function is not even defined at this value. So there are multiple things, there are multiple issues here that result in us not being able to define the derivative. This is an example of a vertical line, a vertical tangent line right here. So we can see how function is defined, function is continuous, looks good. If you want to draw the tangent line, it will be vertical, but vertical tangent lines don't have a slope, therefore this function doesn't have a derivative at x equals 2. This is another similar example. So vertical tangent line means no slope, means no derivative. And we're done with this homework. If you have any questions, please let me know.